Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. The recovery of ancient knowledge often resembles an archaeological dig, with scholars carefully brushing away layers of time and interpretation to reveal the brilliance of past minds. So it was with Aryabhata, whose seminal work, the Aryabhata, remained largely obscured until the 20th century. Early translations presented formidable challenges. Aryabhata's verses, densely packed with mathematical and astronomical insights, demanded both linguistic skill and a deep understanding of the underlying concepts. Unraveling his methods required a meticulous reconstruction of his thought processes, a journey into the intellectual landscape of 5th century India. This era, often referred to as the Gupta period, represents a high point in Indian history. It witnessed a flourishing of art, literature, and science. Under the patronage of powerful emperors, scholars and artisans alike enjoyed an environment conducive to innovation and creativity. In mathematics and astronomy, this period saw significant advancements, laying the groundwork for future generations of Indian scientists. Aryabhata stands as a towering figure of this golden age, his contributions shaping the course of mathematical and astronomical thought for centuries to come. The scope of Aryabhata's extant work is primarily defined by the Aryabhatiya. This compact treatise, composed in verse, encapsulates his mathematical and astronomical theories. Divided into 4 sections, it covers topics ranging from arithmetic and algebra to trigonometry and spherical astronomy. While other works may have been attributed to him, the Aryabhatiya remains the most authentic and comprehensive source of our knowledge concerning his intellectual achievements. It is through this text that we gain access to Aryabhata's revolutionary ideas and his profound understanding of the cosmos. Among Aryabhata's most significant contributions is his refinement of the number system. Existing numerical systems, such as the Roman numeral system, presented considerable obstacles to performing complex calculations. Imagine attempting multiplication or division using symbols such as MCML, XX fort. The cumbersome nature of these systems severely limited mathematical progress. Aryabhata recognized this impediment and envisioned a more efficient and elegant approach. His solution lay in the development of a place-value system, a concept that revolutionized arithmetic and paved the way for modern mathematics. This system, employing 9 numerals along with a symbol for 0, allowed for the representation of any number, no matter how large or small, using a concise and standardized notation. Each digit's position within a number determines its value, with each successive position representing a power of 10. For example, in the number 528, the 5 represents 5 hundreds, the 2 represents 2 tens, and the 8 represents 8 ones. This seemingly simple innovation unlocked unprecedented possibilities for mathematical manipulation. The introduction of 0 as a placeholder is of particular importance. Prior to Aryabhata, the concept of 0 existed in some cultures, but its use as a numeral within a place-value system was not fully realized. 0 provides a crucial function, indicating the absence of a particular power of 10. Without 0, distinguishing between 52 and 502 would be impossible using a place-value system. Aryabhata's inclusion of 0 completed the decimal system, providing a powerful tool for representing numbers and performing arithmetic operations. The impact of Aryabhata's place-value system extends far beyond the realm of pure mathematics. Its adoption facilitated advancements in various fields including commerce, engineering, and astronomy. Complex calculations, previously requiring laborious effort, could now be performed with relative ease. This efficiency enabled scientists and engineers to tackle increasingly complex problems, leading to new discoveries and innovations. The decimal place value system is fundamental to modern mathematics and computing. Every calculation performed by a computer, from the simplest addition to the most complex simulation, relies on the principles established by Aryabhata over 15 centuries ago. Its influence permeates our technological world, shaping the way we quantify, analyze, and understand the universe. Aryabhata's system enabled the efficient execution of fundamental arithmetic operations. Addition, subtraction, multiplication, and division, the cornerstones of mathematical calculation, became significantly easier to perform within his place value framework. Consider the task of multiplying two large numbers. In a non-place value system, this would involve a complex process of repeated additions and conversions. Using Aryabhata's system, the multiplication can be broken down into a series of simpler operations, utilizing the distributive property and the place values of the digits. This streamlined approach reduced the likelihood of errors and significantly increased the speed of calculation. Furthermore, Aryabhata's system facilitated the development of algorithms for extracting square roots and cube roots. These operations, essential for various mathematical and scientific applications, were previously challenging to perform with accuracy. Aryabhata devised methods for approximating these roots, providing practical tools for engineers and astronomers. These algorithms, though refined over time, remain rooted in the principles established by Aryabhata, demonstrating the enduring relevance of his mathematical insights. The adoption of Aryabhata's numeral notation also had a profound impact on the standardization of mathematical communication. Prior to his system, different regions and cultures employed diverse notations, making it difficult for scholars to share and build upon each other's work. Aryabhata's system provided a common language for expressing numerical quantities, fostering collaboration and accelerating the advancement of mathematical knowledge. This standardization facilitated the transmission of mathematical ideas across geographical boundaries, contributing to the globalization of scientific thought. The numerals we use today, often referred to as Arabic numerals, are in fact a direct descendant of the system developed in India, a testament to the lasting influence of Aryabhata's work. The elegance and efficiency of Aryabhata's place value system stemmed from its inherent simplicity and its ability to represent numbers in a structured and organized manner. This structure allowed for the development of standardized rules and procedures for performing arithmetic operations. These rules, easily memorized and applied, democratized mathematical knowledge, making it accessible to a wider audience. Aryabhata's system empowered individuals to engage with mathematics, fostering a culture of scientific inquiry and innovation. The legacy of his contribution continues to resonate in classrooms and research institutions around the world, shaping the way we learn, teach, and apply mathematics. Building upon the foundation of numerical representation, Aryabhata ventured into the realm of trigonometry, a field essential for astronomical calculations and surveying. The mathematics of triangles, particularly right triangles, provided the tools to measure distances, angles, and heights, critical for mapping the heavens and the earth. Existing trigonometric tables in Aryabhata's time suffered from inaccuracies, hindering precise calculations needed for astronomical predictions and land measurements. These tables, often based on empirical observations and geometric approximations, lacked the rigor and systematic approach required for advanced scientific inquiry. Aryabhata addressed this challenge by introducing a novel approach to trigonometry, one that emphasized the relationships between angles and the sides of triangles with unprecedented accuracy. Central to Aryabhata's trigonometric innovations was the concept of the sine function, which he termed jaya. This term, derived from the Sanskrit word for chord, represented the relationship between an angle and the length of the chord subtended by that angle in a circle. Aryabhata meticulously calculated and tabulated the values of the Jaya function for various angles, creating a table of sins that surpassed previous efforts in both accuracy and comprehensiveness. This table, presented in his magnum opus, the Aryabhatiya, became an indispensable tool for astronomers and mathematicians. Alongside the Jaya, Aryabhata also introduced the concept of the Utkramatjaya, or versed sign. The versed sign represents the difference between the radius of the circle and the cosine of the angle. While the sine function captures the vertical distance from a point on the circle to the diameter, the versed sign captures the horizontal distance from that point to the center of the circle. The inclusion of the versed sign demonstrated Aryabhata's deep understanding of the geometric relationships within a circle and provided an additional tool for solving trigonometric problems. The creation of accurate sine and versed sign tables demanded a rigorous mathematical approach. Aryabhata employed sophisticated geometric techniques and iterative methods to approximate the values of these functions. His calculations involved dividing a circle into equal parts and determining the lengths of the corresponding chords. He then used these chord lengths to estimate the sine and versed sign values for various angles, refining his approximations through successive iterations. The precision of Aryabhata's trigonometric tables allowed for a significant improvement in astronomical calculations. Astronomers could now use these tables to more accurately determine the positions of celestial objects, predict eclipses, and refine cosmological models. Surveyors also benefited from Aryabhata's work, as they could use the tables to measure distances and angles with greater accuracy, enabling them to create more precise maps and land surveys. Beyond the practical applications, Aryabhata's contributions to trigonometry also had a profound impact on the development of mathematical theory. By introducing the sine and versed sign functions and providing accurate tables, he laid the foundation for the study of trigonometric functions as abstract mathematical objects. His work paved the way for later mathematicians to explore the properties of these functions, develop trigonometric identities, and apply them to a wide range of problems in geometry, algebra, and calculus. The concept of the Jayas eventually migrated through translations and transliterations. It traveled from Sanskrit to Arabic, where it became Jibba. Later, when European scholars translated Arabic texts, they mistook Jibba for Jayab, an Arabic word meaning bay or inlet. This misinterpretation ultimately led to the adoption of the Latin word sinus, meaning bay, as the term for the sine function in Western mathematics. So the sine, a cornerstone of modern mathematics, traces its etymological roots back to Aryabhata's groundbreaking work on chords in a circle. The sine and cosine functions, descendants of Aryabhata's Jaya and its companion functions, are ubiquitous in modern science and technology. They appear in physics to describe oscillatory motion, such as the swinging of a pendulum or the propagation of waves. Engineers use them to analyze alternating current circuits, design bridges and buildings, and model the behavior of mechanical systems. Computer scientists employ trigonometric functions in computer graphics, image processing, and virtual reality to create realistic and immersive experiences. The modern representation of trigonometric functions, often expressed using Cartesian coordinates and unit circles, provides a powerful framework for understanding their properties and relationships. The sine of an angle is defined as the y-coordinate of a point on the unit circle, while the cosine is defined as the x-coordinate. This geometric interpretation allows for a visual understanding of the periodic nature of trigonometric functions and their connections to the Pythagorean theorem and other fundamental mathematical concepts. The applications of sine and cosine extend far beyond the realm of pure mathematics. In signal processing, these functions are used to decompose complex signals into their constituent frequencies, enabling engineers to filter noise, compress data, and transmit information efficiently. In medical imaging, trigonometric functions are used to reconstruct images from X-ray or MRI data, allowing doctors to diagnose diseases and monitor treatment progress. In finance, they are used to model cyclical patterns in stock prices and other economic indicators, helping investors make informed decisions. Aryabhata's trigonometric legacy extends to navigation. The ability to accurately calculate angles and distances is essential for determining position and charting courses. Modern navigation systems, such as GPS, rely on sophisticated mathematical algorithms that incorporate trigonometric functions to pinpoint locations with remarkable precision. These systems enable ships, airplanes, and even automobiles to navigate safely and efficiently across the globe. The enduring influence of Aryabhata's trigonometric work stems from its combination of mathematical rigor and practical utility. He provided not only a theoretical framework for understanding the relationships between angles and sides of triangles, but also the tools and techniques needed to apply this knowledge to real-world problems. His sine and versed sine tables, meticulously calculated and widely disseminated, became indispensable resources for astronomers, mathematicians, and surveyors for centuries to come. His contributions continue to shape the way we understand and interact with the world around us, underpinning technologies that have revolutionized communication, transportation, and scientific discovery. Aryabhata's legacy extends far beyond the realm of trigonometry, encompassing profound contributions to astronomy that challenged prevailing cosmological views and laid the groundwork for future scientific advancements. His keen observations of the celestial sphere and his innovative mathematical models provided a more accurate and coherent understanding of the universe than had previously existed. During Aryabhata's time, the dominant cosmological model was geocentric, placing the Earth at the center of the universe with the Sun, Moon, and planets revolving around it. This model, propagated by ancient Greek philosophers and astronomers such as Ptolemy, faced increasing difficulties in accurately predicting the observed motions of celestial bodies, particularly the retrograde motion of planets. These apparent backward movements required increasingly complex and contrived explanations within the geocentric framework, burdening the model with epicircles and difference. Aryabhata sought a more elegant and accurate explanation. Aryabhata proposed a system that, while not explicitly heliocentric in the modern sense, represented a significant departure from strict geocentrism. He posited that the Earth rotates on its own axis, completing one rotation approximately every 24 hours. This revolutionary idea explained the apparent daily motion of the stars and provided a simpler explanation for the rising and setting of the Sun. In Aryabhata's model, the planets still revolved around the Sun, but their motion was understood relative to a rotating Earth. This quasi-heliocentric perspective, though not fully articulating a sun-centered system, marked a crucial step toward the eventual acceptance of heliocentrism. One of the most compelling aspects of Aryabhata's astronomical model was his explanation of solar and lunar eclipses. He rejected the prevailing mythical and religious explanations that attributed eclipses to supernatural forces or celestial demons. Instead, Aryabhata provided a rational and scientific explanation, asserting that eclipses are caused by shadows. He accurately described a solar eclipse as occurring when the moon passes between the sun and the earth, casting its shadow on the Earth's surface. Similarly, he explained a lunar eclipse as the Earth passing between the Sun and the Moon, casting its shadow on the Moon. His understanding of the geometry of these shadows allowed him to predict the timing and duration of eclipses with remarkable accuracy, further solidifying the scientific basis of his model. He understood that the size and shape of the Earth's shadow, as well as the Moon's, played a crucial role in determining the characteristics of an eclipse. This departure from mythological explanations toward a purely geometric and physical understanding of eclipses represented a major advancement in astronomical thought. It shifted the focus from superstition to observation, measurement, and mathematical modeling. Aryabhata's genius extended to his remarkably accurate calculation of the Earth's circumference. Using sophisticated geometric techniques and astronomical observations, he estimated the Earth's circumference to be 24,835 miles. This value is impressively close to the modern measurement of 24,901 miles, demonstrating the precision of his methods and the accuracy of his observations. His calculation relied on measuring the angle subtended by a distant star at different latitudes, and then applying geometric principles to determine the Earth's radius and consequently its circumference. Furthermore, Aryabhata made significant contributions to determining the length of the sidereal year, which is the time it takes for the Earth to complete one orbit around the Sun relative to the fixed stars. His estimate of 365 days, 6 hours, 12 minutes and 30 seconds is remarkably close to the modern value. This precise determination of the sidereal year was essential for developing accurate calendars and predicting astronomical events. It required careful observation of stellar positions over extended periods and sophisticated mathematical analysis to account for the complexities of Earth's orbit. Aryabhata's astronomical model, with its rotating Earth, shadow-based explanation of eclipses, accurate estimation of Earth's circumference, and precise calculation of the sidereal year, represented a paradigm shift in understanding the cosmos. While his model retained elements of geocentrism, its innovative features paved the way for future astronomers to develop more comprehensive and accurate heliocentric models. His work challenged existing dogma and promoted a scientific approach to understanding the universe based on observation, reason, and mathematics. It's tempting to view Aryabhata's model through the lens of modern astronomy and point out its imperfections. However, such a perspective overlooks the historical context and the magnitude of his achievement. He worked centuries before the invention of the telescope and other sophisticated astronomical instruments. He relied on naked-eye observations and ingenious mathematical techniques to unravel the mysteries of the cosmos. In comparison, modern astronomy benefits from centuries of accumulated knowledge, advanced technology, and a vast network of global observatories. Despite these advantages, Aryabhata's insights remain a testament to the power of human intellect and the enduring quest to understand our place in the universe. The historical significance of Aryabhata's contributions cannot be overstated. His astronomical model, though not perfectly heliocentric, was a crucial step toward understanding the true nature of the solar system. His explanation of eclipses as shadows cast by celestial bodies demolished centuries of mythological explanations. His accurate calculations of Earth's circumference and the sidereal year demonstrated the power of scientific observation and mathematical analysis. Aryabhata's work influenced generations of astronomers and mathematicians in India and beyond, shaping the course of scientific progress. His ideas, disseminated through his magnum opus, the Aryabhatiya, sparked debate and discussion among scholars, fostering a culture of intellectual inquiry and scientific exploration. While some of his contemporaries and successors may have refined or expanded upon his models, Aryabhata's foundational contributions remained a cornerstone of Indian astronomy for centuries. His emphasis on empirical observation, mathematical rigor, and rational explanation set a new standard for scientific inquiry. Aryabhata's legacy also extends to the development of astronomical instruments and observational techniques. His work inspired the construction of observatories and the creation of more precise instruments for measuring celestial positions. These advancements in turn enabled astronomers to refine their models and improve their predictions. The continuous cycle of observation, modeling and refinement fueled the growth of astronomical knowledge and contributed to a deeper understanding of the cosmos. The impact of Aryabhata's work reverberated across cultures and continents. His astronomical insights, transmitted through trade routes and scholarly exchanges, influenced the development of astronomy in other parts of the world, including the Islamic world and Europe. His emphasis on mathematical modeling and empirical observation helped to shape the scientific revolution that transformed our understanding of the universe. Aryabhata's contributions to astronomy stand as a shining example of human ingenuity and the power of scientific inquiry. His revolutionary ideas, accurate calculations, and rational explanations challenged existing dogma and paved the way for future advancements. His legacy continues to inspire scientists and mathematicians to push the boundaries of knowledge and explore the mysteries of the universe. His work serves as a reminder that even in the absence of advanced technology, the human mind, armed with curiosity, reason and mathematics, can unlock the secrets of the cosmos. The impact of Aryabhata's work reverberated across cultures and continents. His astronomical insights, transmitted through trade routes and scholarly exchanges, influenced the development of astronomy in other parts of the world, encompassing the Islamic world and Europe. His emphasis on mathematical modeling and empirical observation helped to shape the scientific revolution that transformed our understanding of the universe. Aryabhata's contributions to astronomy stand as a shining example of human ingenuity and the power of scientific inquiry. His revolutionary ideas, accurate calculations, and rational explanations challenged existing dogma and paved the way for future advancements. His legacy continues to inspire scientists and mathematicians to push the boundaries of knowledge and explore the mysteries of the universe. His work serves as a reminder that even in the absence of advanced technology, the human mind, armed with curiosity, reason and mathematics, can unlock the secrets of the cosmos. Beyond his groundbreaking work in trigonometry and spherical astronomy, Aryabhata made significant strides in the field of indeterminate equations, a branch of mathematics with profound implications for astronomical calculations and calendar construction. These equations, also known as Diophantine equations, present a unique challenge finding integer solutions to equations where multiple solutions are possible. This was a critical area of investigation, as many astronomical problems reduced to solving such equations to determine planetary positions and reconcile different calendrical cycles. The problem of solving linear indeterminate equations was far from a mere mathematical curiosity during Aryabhata's time. It was an essential tool for astronomers and calendar makers. Accurately predicting the positions of planets and the timing of eclipses required sophisticated calculations that often involved finding integer solutions to equations with multiple unknowns. Furthermore, the reconciliation of different calendrical systems such as lunar and solar calendars also depended on the ability to solve these types of equations. The challenge lay in devising a systematic method for finding these integer solutions, a method that could be applied to a wide range of astronomical problems. Aryabhata's unique contribution to this field was the development of the Kutaka method, also known as the pulverizer. This ingenious algorithm provides a systematic approach to solving linear Diophantine equations of the form at x plus by equals c, where at b and c are integers, and x and y are the unknown integers we seek. The name Kutaka itself suggests the core idea of the method repeatedly breaking down the coefficients of the equation until a solution can be readily identified. The basic principle behind the Kutaka method involves a process of successive division and remainder calculations. Starting with the coefficients a and b, the algorithm repeatedly divides the larger coefficient by the smaller one, obtaining a quotient and a remainder. This process is then repeated with the smaller coefficient and the remainder, and so on, until a remainder of 0 is obtained. The last non-zero remainder is the greatest common divisor of a and b. If the greatest common divisor does divide c, then the equation has integer solutions, otherwise it does not. Once the existence of integer solutions is confirmed, the Kutaka method proceeds to find a particular solution using a process of back substitution. The quotients obtained during the successive divisions are used to express the original equation in terms of the remainders. By working backwards through these equations, a solution for x and y can be found. This particular solution can then be used to generate all other integer solutions to the equation. To illustrate the application of the Kutaka method, consider a simplified example. Suppose we want to solve the equation 5x plus 3y equals 1. Applying the Kutaka method, we first divide 5 by 3, obtaining a quotient of 1 and a remainder of 2. Next, we divide 3 by 2, obtaining a quotient of 1 and a remainder of 1. Finally, we divide 2 by 1, obtaining a quotient of 2 and a remainder of 0. The last non-zero remainder is 1, which divides 1, confirming that the equation has integer solutions. Now working backwards, we can express 1 as 3 minus 1 times 2. Substituting 2 equals 5 minus 1 times 3, we get 1 equals 3 minus 1 times the quantity, 5 minus 1 times 3, which simplifies to 2 times 3 minus 1 times 5. Thus we have found a solution x equals -1 and y equals 2. This is a particular solution, and all other integer solutions can be generated from it. The true power of the Kutaka method lies in its ability to solve more complex equations arising from astronomical problems. For instance, determining the time of a future planetary conjunction might involve solving an equation relating the orbital periods of the planets. The Kutaka method provides a systematic way to find the integer solutions that correspond to the times when the planets will be in conjunction. Similarly, the Kutaka method proves invaluable in calendar calculations. Different calendrical systems such as lunar and solar calendars have different cycles. Reconciling these cycles, for example, determining when a lunar month will coincide with a particular solar date, requires solving linear Diophantine equations. The Kutaka method provides the means to find the integer solutions that represent the times when the cycles align. The Kutaka method represents a significant advancement in the history of mathematics. It is one of the earliest known algorithms for solving linear Diophantine equations, and it demonstrates a deep understanding of number theory. Aryabhata's method was not merely a collection of rules, it was a systematic and elegant approach that could be applied to a wide range of problems. The influence of the Kutaka method extended far beyond Aryabhata's own time. Later Indian mathematicians, such as Brahmagupta and Bhaskara, further refined and generalized the method. Their work built upon Aryabhata's foundations, leading to even more powerful techniques for solving indeterminate equations. The Kutaka method also found its way to other parts of the world, influencing the development of number theory in the Islamic world and Europe. Aryabhata stands as a pivotal figure in the history of mathematics and astronomy. His contributions to trigonometry, spherical astronomy, and indeterminate equations represent a remarkable achievement for his time. His work demonstrates a deep understanding of mathematical principles and a keen ability to apply these principles to solve real-world problems. His influence on later mathematicians and astronomers, both in India and globally, is undeniable. Aryabhata's legacy extends beyond the specific mathematical and astronomical results he obtained. His emphasis on mathematical modeling, empirical observation, and rational explanation helped to shape the scientific tradition in India. His work serves as an example of the power of human reason to unlock the secrets of the universe. Studying historical scientific advancements, such as those made by Aryabhata, is of paramount importance for understanding the evolution of human knowledge and the nature of scientific progress. It allows us to appreciate the ingenuity and creativity of past scientists and mathematicians, and to see how their ideas have shaped our current understanding of the world. It also provides valuable insights into the process of scientific discovery, highlighting the importance of observation, experimentation, and mathematical reasoning. Furthermore, it reminds us that scientific progress is a cumulative process, with each generation building upon the work of those who came before. By studying the history of science, we can gain a deeper understanding of the nature of scientific knowledge and the process by which it is acquired. This understanding is essential for fostering scientific literacy and promoting scientific inquiry in the present day. We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.